This is lecture 7, part 1, and I will start computer vision. And computer vision is basically how to deal with images. So suppose the input are images. What are some of the special algorithms to deal with those types of inputs? So as usual, I will start the first part with some examples, but this time some actual real-life applications to computer vision instead of those like cat, dog, dragon stuff. So let's get started. And instead of going through the list, it's hard to show these by just talking about them. So let me show you some actual demos. And all the links are on my website. Let's start with image segmentation. Image segmentation is basically you have an image, you want to know which pixels correspond to the bicycles and which pixels correspond to a person. So the main problem is basically given a pixel, how do you label this pixel or classify this pixel as either the bicycle class or the person class or not these two classes? One important thing is you need to know the value of the neighboring pixels in order to do this. And sometimes you also need to know the label of the neighboring pixels. So it's very important thing is that the label depends on the neighbors. Okay, so that's the first example. And you can actually try to input your own image and get it segmented. And let's go to the next one, image colorization. So that should be an obvious application. You have a black and white image like this, and then you want to color it. And so the idea is still the same. Given a pixel, you want to classify the pixel as, say, one of the multiple colors other than black and white based on the pixel intensity, and also, again, based on the neighboring pixels. That's an important theme of computer vision. So here you can try it yourself as well. You have a black and white photo. I don't know why you have those, but if you have, you can make it a colored photo. Okay, so next, image reconstruction. So that one is an interesting one. So if you look at this here, if you want to make the person look younger, you can just remove parts of the image and let the algorithm reconstruct that part. So he may look younger, and also it can be used to remove a mustache like this. It's actually very good. So if you compare this with what happened with Superman in Justice League, well, I don't actually know what happened in the movie, why the visual effects is like bad, but it's kind of an algorithm that can do this. And also, if you want to remove someone else in your photo, you can do something like this. You can just erase this part and use the algorithm to automatically generate something that's not a person. So that would be something interesting. And again, you can try it yourself as well. And let me move on to the next one. Drawing to images. So here I need to check the box. And let's actually try to draw something. Let's draw some cloud here. And I'm drawing using a mouse, so it's going to be really bad. And maybe let's draw a house on top of the water. And maybe we need a roof. What else do we need? There's a sand, so let's draw something like a sand beach. And at the end, I'll draw a tree in the water. So hopefully this looks like a tree. Well, I know that this drawing is really bad. Let's see if it can be generated. Okay, so that's actually okay. So the sand looks like okay. The tree looks good. It looks like a tree in the water, and the house is like not great, and the roof is not great, but the cloud is really good as well. So it's basically generating pixel values based on the drawing. So it's kind of similar to the colorization problem. It's still classifying each pixel as kind of some other color based on the class. So let's close this. And next, style transfer. So style transfer is basically you have a style image, and you have another image that you want to apply that style. So here the background is the style, and these 4 images, for example, are the images you want to apply that style. It takes a while to run or activate the network, and it generates an image using this style, and it's your image. And actually here you can try your own image as well. So I think on this website you cannot use your own style because it takes too long to train these things based on a style. But in the other link that I shared in this one, I think you can provide your own style as well, but it will take a long time to run. Okay, that's another example. We'll talk about YOLO at the end. And the next one is the post estimation. And here, the important part is not finding an image with the same pose. It's actually finding the pose. So basically, the task here is to figure out where your eyes are, where your arms are, and where your legs are, and create basically a skeleton like this so that we can search for other images and find images with the same pose. So this is related to something called a deformable parts model, and I think it's covered in computer vision, so it's 766 in our school, and maybe not last year, but maybe in the future. So I will actually not go through models like this, but it's just something that a computer vision algorithm can deal with. So let's move on to the next one. Next one is actually called pose estimation. So it's if you have multiple people you want to estimate their pose, and it's basically the same task. Okay, so at the end, we will talk about YOLO, which I opened here already. And YOLO here stands for you only look once, not you only live once. So basically the idea is you only look at a pixel once through the picture, and then you can recognize the object. So here, in the video, this person is classified as a person, but this person is classified as not a person because there is a adversarial patch. So if that's removed, that person actually is labeled as a person. But if you have this patch, basically a small image, then it becomes not a person again. So it's kind of like a tag of a computer vision algorithm. So I think, yes, so if you move the patch to the other person, that other person will no longer be classified as a person. So it's basically some kind of way, some kind of specific image to hack a computer vision algorithm. So if we have time at the end of the course, when we talk about game theory, we will talk about some theoretical models related to this, but possibly not. So I will not promise anything. So let's get back to our slides. And which examples do we not go through? The super resolution one, from the name, it should be clear that we want to increase the resolution, so make images more clear. And image captioning should be very clear as well. It's just if you have an image, you want to say what's in the image, and basically, other than recognizing objects, you want to recognize the action, their relationship, and so on. So that's captioning. And we talk about most of these. And visual question answering is basically given the image, the computer can figure out like how many people are there in the image, and say basically can answer questions. So this is also related to natural language processing. And the last one, medical image analysis. So it's related to medical images, obviously. And one thing that may be special with medical images is that they are 3D images. So instead of pixels, they have voxels. So it would be something like the small blocks in Minecraft. And so you have the color of a voxel, a 3D pixel, and then based on those 3D pixel intensities, we can figure something out. We'll actually talk about this in the next lecture. Okay, so that's all the real life examples that I want to go through. And I guess we noticed something that's important to computer vision tasks is that we want to know the relationship between pixels and their neighbors. So far in the previous lectures, we're assuming all the pixels or all the features which are pixel intensities, they are independent. So we have different weights for those pixels. And here, for these tasks, we don't want to do that. So we want to know where this pixel is and what are the neighboring pixel values. So we're going to do something similar, but let me show you with a simple diagram. So suppose we have an image like this. And what we are doing here is, what we were doing is we have 1, 2, 3, 4, 5, 6, 7, these things as features. And each feature is associated with a weight, and this is weight 2. And this is not efficient because we are assuming that pixels 1 and 6, they're not related, but they are. So what we want to do is we want to somehow summarize the pixel intensities in a region. And hopefully we can figure out, say, whether this region correspond to an edge, correspond to a blob, or something like that. And we want to put all of these as one feature value. So this region, say, is our feature 1, and we want to somehow combine it in a simple way. And maybe this region, let's combine it to another feature, feature 2. And it seems the simplest way is to use some kind of two-dimensional dot product. And indeed, that's actually what we'll do. And basically, linearly combining pixels and weights in a rectangular region is called convolution. So we will start with what exactly is a convolution. So of course, we'll start with one-dimensional convolution, which is the simplest. We will have a new notation. So remember, dot product is just x dot w. And here it's just at, I mean, not at, this is the star. So x star w. So I usually read it as x convoluted with w. And we will have a new name for w. Instead of weights, we're going to call it like filter. And usually in other computer vision courses, they are called kernels. But the problem here is that kernels are used for SVMs already, so I don't want to confuse people. So personally, I'm going to use filter instead of kernels. And the idea here is if you actually look at the formula, we are doing dot product, right? So suppose we have a vector x, and we want to somehow convolve it with the w. So it's kind of dot product, but in the reverse way. So one is t, one is j minus t. So you should try some example with this formula, by the way. So it's basically the first element multiplied by the last, middle multiply middle, and last multiplied by the first. So effectively still a dot product. It's just the weights are reversed. And what we're doing here is the dot product of the filter and x for the first 3, for the next 3, and then for the next 3. And then for each one, we get a, say, a z, z1, z2, and z3. And of course, we can put some activation function on top of this. So it becomes a1, a2, and a3. Basically, we're constructing some kind of new features based on the convolution between our original image and some kind of weights. And of course, we can extend this to the two-dimensional case. And the formula again, it looks like dot product again. So it's just element-wise multiplication. And let me actually show you in a diagram. So let's draw the same diagram as before. And suppose we have a simple 3x3 filter. So these are the weights, and this will be our input x. And this is a weight 1, weight 2, and weight 3. And what we're going to do is do the dot product again. So let's do it for the first region, which is this one. So we use the first weight to multiply by this, and second weight to multiply by this and this. So remember, it's in reversed. So there are some kind of physics-related representation or explanation why it is multiplied in reverse, but we don't really care here. And multiplying every term like this. So if you basically do dot product of this rectangle or this square with this weight square, you can get one number, and that number will be our feature number 1. Or maybe you can call it activation number 1. And then we can do the same thing with the next block. So do the multiplication, and then it will generate another number. We'll call it feature number 2. And similarly, the third one, we'll call it feature number 3. So this is basically the convolution between x and w. So it may seem very simple. It's actually very simple to implement as well. But there are some technical problems with this. So the first one is that if you do exactly this, this is a 5x5 image. After convolution, it will become 3x3. So maybe we are wasting some of the pixels, maybe. So we may want to add zeros like surrounding this image. And when we do convolution, we also include this. So this will be a 3x3 patch. And if we convolve with this weight here, you'll get an extra feature, say F0 here. And what this is called zero padding. So you are basically padding 0 around the image so that you can get the same number of activations compared to the same number of pixels in the image. So of course, without this, what we did is called no padding. And there are other ways or other values you can pad these, but we're not going to talk about those. And the other thing that we just automatically assumed is we're moving 1 pixel each time. So here we're doing this square, and then the next square we're doing is just move 1 pixel to the right, and then we move another pixel to the right. But if we want to skip pixels, for example, we want to do two pixel move at a time, then we do the first one, and then we move 2 pixels and do the next square directly. So the number of steps, let's write the number of pixels per step, that's called a stride. So a stride of 1 would be what we were doing, and a stride that's equal to the size of the filter. So for example, a stride of 3 would be non-overlapping. So these small squares will not be overlapping on the image. So here there are only 5, so it's hard to show you this. But if you look at the first one, and if you move 3, then it will be a square like this. So none of these squares will be overlapping. And all of these are summarized here in the next slide. So what we're going to do next is we are going to introduce some of these special filters you can use for special purposes, kind of special features you can get from an image, like where are the edges and where are the blobs and so on. And in the next lecture, we'll talk about how to use a neural network to actually train these filters.